All right, so today I'm going to be discussing vectors and level curves for this function that we have. F of x, y is 5 minus 2x squared minus 2y squared. So first they want the vector perpendicular to the level curve of f at negative 1, 1. So level curve means contour diagram, which means that we are going to isolate this function, which is of 3 variables, into only 2 variables, so we can look at it in 2 dimensions. So to find the gradient vector, it is going to be just a normal vector, except the coefficients are the partial derivatives with respect to that variable. So our first step is going to be to find partial x, which is just the derivative with respect to x. And for this function, that means that we view everything that's not in terms of x's, like this y, as a constant. So the derivative of those is going to be 0. So the derivative of 5 with respect to x is 0. Derivative of 2xy squared with respect to x is 0. And then of 2x squared, this derivative is going to be negative 4x. And then using the similar rules for the partial derivative with respect to y, we're going to get the partial derivative with respect to y is negative 4y. So now we are going to take this information and just put it into our vector. And so we're going to have negative 4xi minus 4yj, and that's our gradient vector, but we are given the point negative 1, 1, so we're going to find del f of negative 1. Is it negative 1, negative 1? Excuse me, made a mistake with that. And so this is going to be 4i plus 4j. And this is our vector for this. And so now in part A, we are also asked to draw the level curve. And then to indicate the direction of the perpendicular vector. So now I'm going to use my graph paper for this. And I'm just going to draw a circle that intersects the point negative 1, negative 1, which is right here. So just a circle, because this function is ultimately a paraboloid in a negative direction. So all right, perfect. And now our vector is 4i plus 4j, so it is going to look exactly something like this. All right, so now for part B, we are going to draw 3 additional level curves to the one that we already have. So we're going to draw these level curves by setting z equal to different values so that we can look at this 3 variable function in 2 dimensions rather than 3 dimensions. So I am going to set z at values of negative 3, negative 13, and negative 45, and I chose these numbers so I could graph this easily with pretty radiuses. And then if I replace z with those numbers, then I'm going to get negative 3 equals negative 5 minus 2x squared minus 2y squared. And so from here on, it's just filling in these values and then doing some algebra. So I'll go ahead and do that off camera and then come back. All right, and now I have these values, and then for our equation of a circle, all of these are going to have this as their radius, except this is the squared value of the radius. So for this z value, r is equal to 2, this one r is equal to 3, and this one r is equal to 5. So let's go ahead and graph those. First off, we'll start with r equals 2 for the value of z equals negative 3. And so it's just going around here, creating this circle, and then I am going to label right here z equals negative 3. It's a bit hard to see, but have faith. It is there. I wrote it. All right, I'm going to draw the next two curves and then show the final picture and move on to part C. And then for these, here are the rest of those level curves, and they're a bit hard to see. So for the one with a y-intercept of 5, z equals -45, for 3, z equals -13, for 2, z equals -3, right? And there are our contour diagrams. All right, so now I've been asked to calculate a vector perpendicular to the surface of our function at this time in a three-dimensional plane, at -1, -1, 1. So it is going to be a very similar step to this first problem where we were just finding a vector perpendicular to the level curve, except now we are in 3 dimensions. So for f of xy rather, I should say, we know our function 5 minus 2x squared minus 2y squared. So for our purposes, to calculate a gradient vector for 3 dimensions, we are going to look at this as, instead, 5 minus 2x squared minus 2y squared minus z equals 0 equals big F of x, y, z. So now this translates very directly into our gradient of f of x, y, z, which is then just going to be the partial derivatives of these functions. So it is again -4xi, -4yj, and for k, our derivative is simply -1, so -k. And so now to find the vector at those points, we are simply going to, oh, this should be big F. We are simply going to del of big F x, nope, del of big F of -1, -1, 1. And this is just going to be +4i plus +4j minus k. And this is our normal vector. All right, so after that, for part C, it asks to look at a sketch of the entire surface. And so I've drawn that. It's just an upside down bowl with its maximum at 5, which is just where its vertex is. And so here we have that. It would be difficult for me to draw the point that I'm specifically, or the vector that I'm looking at from this point, because it is on the far side of this paraboloid that I've drawn. So I drew this side, which is from the x and the y portion, and let's erase the vector that I've already drawn. And so it is 4i, 4j minus k, which is going to have a very, very gradual slope, kind of just the direction into the paper. So it is almost impossible for me to draw, but just imagine a vector going back into the paper in that direction, and that is where our vector is. And then for part D, we are just comparing this level surface, or this entire surface, excuse me, to the level curves that I made earlier. And so if you look at this, you could imagine that you're looking down at this from the top, from the z direction, and you know, you kind of just see the function just spreading out as it gets larger, or I mean, as z gets smaller, because the further down, the further negative z gets, the wider our paraboloid is going to open and the larger the radius is going to be. So it does make sense visually looking at these that they belong to the same function. All right, so for part E, we've been asked to compare the gradient vector from problem 2, which is drawn on my graph right here in the middle, to the vector, a vector, tangent to the path at the point -1, -1, 1, which we can see what would be perpendicular. So whatever vector is perpendicular to that one is going to be tangent. And we can kind of imagine it running along this surface. So if we had something tangent to this point, which is -1, 0, +1, it would be somewhat very steep in a direction somewhat like this. And so that's how that vector would look, being tangent to the path. And if we kind of think about those together, this vector versus this other gradient vector. So this one, which is tangent, and this one, which is gradient, this one shows the direction of the rate of change, which is going to be inwards towards the center, because that's where our highest point is, with a y value of +5. And then for our tangent, it is simply going to run along. However, the slope of our tangent line still gives us that average rate of change, so it does make sense that our tangent is also going to point somewhat towards that top, just because it is running along that surface, so it is going to follow the trends that the surfaces have. All right, so for part F, we are asked to calculate vector n perpendicular to our surface at the point -1, -1, 1, and we have already found this in step 3, but let's go ahead and find it again. So a vector perpendicular to a surface is going to be our gradient. So we can look at f of xy equals 5 minus 2x squared minus 2y squared. And we can go ahead and rearrange this so we can manipulate it as big F of x, y, z. And so this is going to be 5 minus 2x squared minus 2y squared minus z equals 0. With this f of x, y being z. If we move it over here, it would be negative, and there we go. We could draw it as simply z. So now from here, our gradient vector is going to be just those partial derivatives of those different components. So -4xi minus 4yj, and then our derivative, our partial derivative with respect to z, is just again going to be -1. So then it is -k. All right. So from here, we're just going to find del f of -1, -1, 1, and it is 4i plus 4j minus k. And so there is that one that we have, and now we are asked to find a vector t, which is actually now going to be tangent to the curve. So it's that vector that we were talking about earlier. But basically, we already have our vector that is perpendicular. So for our vector that is tangent, it is going to be parallel to that point. So we can use the dot product to find t, because we know that it is going to be that its dot product with our normal vector is going to equal 0, since they are perpendicular. To start off, we know that t is going to be 4i plus 4j, and then we know that we are just going to need to find an a to put for that k value. And this is kind of just because we have the same vector for on our contour diagram, so we know no matter what, this is its xy direction. the variation is just going to lie within that k direction. All right, so let's get to finding a. So let's find, this is equal to n, so n dot t is going to be 4 times 4 plus 4 times 4 plus -1 times a, and this is going to equal 0. So we get 16 plus 16 minus a equals 0, and then a equals 32. So now we can fill that back in, and we get the vector tangent to the point -1, -1, 1, 4 on the surface of this function is 4i plus 4j plus 32k. All right, and that is all that I have for you guys today. Perfect.